Welcome to the lesson on the refrigeration cycle. We have talked about many aspects of the various HVAC system configurations you could encounter, but we haven't talked about them all. For instance, up until this point, we have just assumed the chiller maintains a constant chilled water supply temperature at set point. But we haven't talked about the inner workings of the chiller and how it actually performs that function. I'll give you a hint. Such chillers utilize the refrigeration cycle. Additionally, in almost all system configurations you have seen thus far, we have discussed the cooling coils as water to air heat exchanger configuration. However, there are many systems out there which have a refrigerant to air heat exchanger serving as the cooling coil. Such systems are called direct expansion or DX systems. But how do these work? I'll give you another hint. They utilize the refrigeration cycle. So pause this lesson now, get a cup of coffee, and do some stretches, because we are about to dive into the weeds of the inner workings of the HVAC industry's leading workhorse, the vapor compression refrigeration cycle. The objective for this lesson is for students to comprehend how the refrigeration cycle is controlled to provide cooling under various loading scenarios. The corresponding samples of behavior will be: identify the four major components of the refrigeration cycle. Identify refrigeration cycle process lines on the pressure enthalpy diagram. Describe and explain the importance of superheat. Outline how the thermostatic expansion valve uses differential pressure to control superheat. Identify the controlled variable in various direct expansion applications. And summarize the various part load capacity controls frequently used in the refrigeration cycle. The refrigeration cycle is used everywhere in HVAC systems. Chillers, heat pumps, and DX or split systems all have the refrigeration cycle at the core of its operation. The invention is such a foundation of our profession that we should have a working knowledge of how the cycle is controlled to handle various loading scenarios. A better understanding of the cycle's control will set the stage for the upcoming lesson on chillers. The refrigeration cycle has evolved since Willis Carrier's first invention in 1902. The technology is constantly improving, but the fundamental principles have remained the same. We can compare the change in the HVAC industry to the evolution in the automobile industry. Cars have changed drastically since Henry Ford's Model T over 100 years ago. They now come equipped with automatic transmissions, cruise control, anti-locking brakes, and a whole host of other improvements. But if your son or daughter asked you how a car works, the science behind the internal combustion engine hasn't changed in the past 100 years. In the same way, the refrigeration cycle fundamentals are the same today as they were in 1902. In this lesson, we're going to dive deep into the cycle to fundamentally understand how the expansion valve controls total cooling capacity. We'll end with explaining some of the newer technologies that make control easier. Along the way, we'll discuss how the equipment is controlled at the HVAC system level. We will get technical, but hopefully by the end you will feel more competent and confident with respect to this topic. Let's start by briefly reviewing the refrigeration cycle you learned about in WENG 460, which will lay the foundation for the rest of our discussion. If you need a deeper review of the refrigeration cycle, the lesson from WENG 460 has been made available to you. The laws of nature dictate that heat will travel from a hot to a cold environment. If we were to drop a watermelon off the top of an Empire State Building, it would fall effortlessly 102 stories before smashing into a great number of pieces. This is because gravity forces the watermelon down. It's the law of physics and can't be changed. In a similar manner, heat has a natural direction of flow. It always travels from a high temperature to a low temperature. We could force the watermelon to travel against gravity, but that would require an input of work by trekking up the 1,860 steps. We can move against Mother Nature, but work is required. Likewise, it is possible to move heat from a cold environment to a hot environment, but it requires work to overcome the forces of nature. Another physical reality we are familiar with is the energy associated with phase change. If you placed a thermometer in a pot of water and boiled the water, you would see the temperature gradually rise as the burner added heat. When the water reached 212 degrees Fahrenheit, it would remain constant as the water boiled and turned into steam. The energy required to convert the water from a liquid to a vapor is called the latent heat of vaporization. The energy that must be absorbed by the water is significant, and during the phase change, the temperature remains constant. For water, the phase change from liquid to vapor occurs at 212 degrees Fahrenheit when the pressure is 14.7 psi. But it is possible to make this phase change happen at a different temperature. If we increase pressure, the boiling temperature also increases. Likewise, if pressure is reduced, the corresponding boiling temperature decreases. As an example, if pressure reduced to 10 psi, the new boiling point of water is 193 degrees Fahrenheit. Therefore, it is possible to force a phase change at a desired temperature by modulating the operating pressure. This is exactly what the refrigeration cycle does. In the refrigeration cycle, pressures are chosen such that the refrigerant boils at the temperatures we desire. In order to move heat into the evaporator and out of the condenser, we need the evaporator to be colder than the air blowing over it, and the condenser to be hotter than the air it's rejecting to. As an example, we might choose pressures such that the refrigerant's temperature is 35 degrees Fahrenheit in the evaporator and 130 degrees Fahrenheit in the condenser. Since heat travels from a hot to a cold environment, this allows the evaporator to absorb heat in a 70 degree Fahrenheit room and the condenser to reject that heat to the 100 degree Fahrenheit outdoor environment. The fact that the refrigerant temperature remains constant during phase change is important because it allows the refrigeration cycle to continue to transfer energy without decreasing the temperature difference between the two fluids. Let's briefly review what is occurring in the refrigerant at each point in the cycle. In doing so, we will introduce a tool you may or may not have seen before, the pressure enthalpy diagram. Trying to remember which of the three phases the refrigerant is in at each point in the cycle, whether it's a liquid, vapor, or a liquid-vapor mixture, is initially difficult. One tool that engineers often use to visualize the refrigeration cycle is the pressure enthalpy diagram. On the pressure enthalpy diagram, the y-axis is pressure in psi, and the x-axis is enthalpy, BTUs per pound. Enthalpy is the measure of energy stored in the refrigerant per unit mass. The dome on the diagram represents the different phases of the refrigerant. Refrigerant on the left side of the dome is in the liquid stage. To the right of the dome is the vapor region. Inside the dome is the liquid-vapor mixture region. Inside the dome, some of the refrigerant is liquid and some is vapor. If you think back to our previous example, this is the point where the water is boiling. Water molecules are boiling off and becoming steam, but there is still water in the pot in liquid form. Remember, as the phase changes between liquid and vapor, this process occurs at a constant temperature. We refer to this temperature as the saturation temperature. Though this particular plot is not for water, we have previously talked about how, at 14.7 psi, the saturation temperature of water is 212 degrees Fahrenheit. This chart depicts that temperature remains constant inside the saturation dome, and what that temperature is depends on the pressure the mixture is operating at. Notice that inside the liquid-vapor region, changes in enthalpy occur at a constant temperature. Let's overlay the refrigeration cycle process onto the pressure enthalpy diagram and look at how that corresponds to each point on the cycle. The numbers shown on the pressure enthalpy diagram correspond to the points shown on the refrigeration cycle. We'll start at the entrance of the evaporator, point 4. Cold liquid refrigerant travels through the evaporator where warm zone air is blowing over the heat exchanger. As the refrigerant absorbs heat, the enthalpy increases, causing the refrigerant to change from a liquid to a vapor. In other words, the refrigerant evaporates, which is why we call this heat exchanger the evaporator. When the refrigerant leaves the evaporator, it is now 100% vapor. It is important that the refrigerant leaving the evaporator is indeed 100% vapor. This prevents liquid from entering the compressor. Since liquid is an incompressible fluid, flooding the compressor runs the risk of damaging this expensive component. The cycle is controlled to make sure refrigerant entering the compressor is entirely vapor by looking at the cycle's superheat. Superheat is the increase in refrigerant temperature above saturation temperature. Let's look at an example to make sure we really understand superheat before moving on. R22 is traveling through an evaporator with an operating pressure of 45.3 psi. At this pressure, R22 saturation temperature is 22 degrees Fahrenheit. Initially, most of the refrigerant is a liquid, represented by the dark blue color in the evaporator. As refrigerant moves through the evaporator, heat is absorbed from the room, causing liquid refrigerant to boil into a vapor. In this image, the light blue area represents R22 in vapor form. While refrigerant is boiling, the temperature remains a constant 22 degrees Fahrenheit. At point A, the final liquid molecule has boiled into a vapor. R22 is now a saturated vapor. At this point, additional heat absorbed will increase the temperature. The vapor temperature increase above saturation temperature is called superheat. If R22 is 32 degrees Fahrenheit at 45.3 psi gauge, it has a superheat of 10 degrees. Superheat is necessary because it ensures no liquid refrigerant enters the compressor. On the other hand, if the superheat is too high, the AC unit will run inefficiently. When technicians charge the refrigeration cycle, they look at the cycle's superheat to validate the right amount of refrigerant has been added. Superheat varies from unit to unit, but typically it's on the order of 10 degrees. Refrigerant flow to the evaporator is controlled to keep the superheat constant. We'll talk more about how this is controlled in a little bit. After the evaporator, the refrigerant, now in vapor form, travels to the compressor. As the refrigerant is compressed, the pressure increases from point 1 to 2. This is where the necessary work to overcome the forces of nature is accomplished. When the refrigerant leaves the compressor, it is now a high pressure, high temperature vapor. At this point in the cycle, the refrigerant has all the energy that was absorbed in the form of heat from the evaporator, as well as the energy added in the form of work from the compressor. We need to release this energy before we can absorb more heat. As refrigerant moves through the condenser, heat is rejected to the outdoors. The enthalpy decreases, and the refrigerant passes completely through the liquid vapor region until all the refrigerant condenses into a liquid. We've now released all the heat the refrigerant absorbed in the evaporator, but the refrigerant is still a high temperature because the pressure is high. In order to lower the temperature, the pressure needs to decrease. In the last step, the refrigerant travels through the expansion valve, where the pressure decreases back to the evaporator's operating pressure. As the pressure decreases, so does the temperature, which allows the evaporator to pick up more heat from the indoors. The refrigerant is now a liquid-vapor mixture where it enters the evaporator and the cycle continues. The refrigerant cycle, shown on the pressure enthalpy diagram, is scalable. Whether the cooling load is 1 ton or 100 tons, the cycle follows the same shape. The 4 process lines on the pressure enthalpy diagram look the same, but the cooling load is constantly changing. How is it then that the AC unit responds to varying cooling loads? The answer is by modulating the flow of refrigerant into the evaporator. Recall that the x-axis of the pressure enthalpy diagram is in units of BTUs per pound. The total energy absorbed in the evaporator is equal to m dot times delta H, where m dot is the mass flow rate in pounds per hour, and delta H is the change in enthalpy. If we change the refrigerant flow rate, or pounds per hour, the total net cooling in BTUs per hour also changes. So let's look at how the refrigeration cycle changes refrigerant flow rate. The expansion device in the refrigeration cycle modulates the flow of refrigerant to the evaporator in response to the cooling load. There are a variety of expansion valves, but this lesson will focus on one of the more common, the thermostatic expansion valve. This might be the most complicated control process we discuss in this course, so bear with me. We will take this in bite-sized pieces and then end with an example which should help clarify how the valve modulates based on the cooling load. The thermostatic expansion valve is designed to maintain constant superheat irrespective of evaporator pressure or cooling load. In other words, as the cooling load changes, the thermostatic expansion valve should adjust the refrigerant flow rate to maintain constant superheat. As a reminder, superheat is the vapor temperature increase above the saturation temperature in the evaporator coil. Now, while our goal is to control superheat, we accomplish this by a combination of pressures acting on the valve. I will explain how superheat and pressure are related, but first let's look at the pressures acting on the thermostatic expansion valve. There are three pressures acting on the valve: the sensing bowl pressure, evaporator pressure, and spring pressure. These three pressures exert three forces on a diaphragm located at the top of the thermostatic expansion valve. When the diaphragm moves, the valve opens and closes. As the valve opens and closes, the refrigerant flow rate changes. The sensing bowl pressure exerts an opening force on the valve. The evaporator and spring pressures exert forces in the closing direction. As you can see from the image, if bowl pressure is greater than the evaporator and spring pressure, the valve will open. If P bulb is less than P evaporator plus P spring, a closing force acts on the diaphragm, moving the needle back to the resting point and restricting the flow of refrigerant. If P bulb is equal to P evaporator plus P spring, the forces are balanced and the valve will remain in its current position. This is an example of proportional control. As the pressure difference between the opening and closing forces increases, the valve displacement changes proportionally. Let's identify the key components of this closed control loop. The measured variables in this closed control loop are the sensing bulb and evaporator pressures. Because we have two measured variables, we also have two sensing elements. In this case, the sensing elements are the bulb's sensor and the valve's diaphragm. The bulb pressure is pushing down on the diaphragm and the evaporator is pushing up. These two forces generate a pressure difference across the diaphragm. This differential pressure is the sensed variable. So we can say the diaphragm sees an input of two measured variables, bulb and evaporator pressure, and outputs one sensed variable, differential pressure. The controller in this loop is the thermostatic expansion valve, and the set point is the spring pressure. When the differential pressure across the diaphragm exceeds the spring pressure, the diaphragm will move down. The control signal, which moves the control device, is the differential pressure. What makes this control loop confusing is the control signal is the same as the sensed variable. The diaphragm is sensing differential pressure, and it's that same differential pressure that actually moves the valve. The control device is the valve needle, which moves up and down based upon the control signal. The manipulated variable is the refrigerant flow rate. As refrigerant flow into the evaporator increases or decreases, the heat transfer rate changes. The evaporator heat transfer is the process plant in this control loop. This process plant changes the sensing bulb and evaporator pressures. The sensing bulb and evaporator pressures are the controlled variables. Really, we are trying to control for superheat, but we control for that by indirectly looking at these pressures, as the difference in these pressures correlates to superheat. Now, I realize this is likely confusing initially. Don't get caught up on the details here. It took me about a dozen attempts to break down each step of this control loop. I don't expect you to recreate this from memory, but I've included it here for your future reference to help clarify the control sequence. It may be helpful to review this loop after you become more familiar with the thermostatic expansion valve. Now we've spent the last few minutes talking about the differential pressure acting on the diaphragm. But remember, our ultimate goal is to control the cycle's superheat. Before we walk through a few examples, we need to understand how differential pressure correlates to superheat. The valve spring pressure is typically set by the manufacturer. Some valves fix the spring's pressure, while others are adjustable in the field. Once installed, the spring pressure remains constant and sets the superheat temperature in the cycle. This will become clearer in a moment. The evaporator pressure isn't constant, but fluctuates with indoor temperature. Further discussion on the varying evaporator pressures is outside the scope of this course. But if you want to learn more, I recommend seeking out an HVAC technician whom you respect and asking them to explain it to you. The bulb pressure will also change as the cooling load varies. Remember that while we are operating inside the liquid vapor region on the pressure enthalpy diagram, the conversion between liquid and vapor occurs at a constant saturation temperature. Because of this, we can correlate the evaporator's operating pressure and temperature. Shown here is the relationship between pressure and saturation temperature for R22. HVAC technicians are well versed in these tables, as they use them to charge refrigerant and troubleshoot problems. This pressure-temperature relationship is what allows the thermostatic expansion valve to use pressure inputs to control superheat temperature. The sensing bulb is installed at the end of the evaporator coil after refrigerant has evaporated into a vapor. In the image to the right, the darker colored portion of the evaporator represents vapor and the lighter color represents liquid. The bulb is sensing the temperature of the refrigerant at this point. Inside the bulb is a small amount of refrigerant called the thermostatic charge. The thermostatic charge can be a variety of substances, but in this example we will assume it is R22. The manufacturer installs R22 such that the refrigerant always operates in the liquid vapor region, meaning some of the refrigerant in the bulb is in liquid form and some remains in vapor form over all the operating conditions. The bulb temperature is the same temperature as the evaporator at the point it is measuring, which in this case would be at the discharge of the evaporator. Because the thermostatic charge operates in the liquid vapor region, the corresponding bulb pressure is dictated by the R22 pressure saturation temperature table. It is probably easiest to understand bulb pressure by looking at an example. Let's assume the evaporator's exiting temperature is 35 degrees. Because the sensing bulb is in direct contact with the evaporator at its discharge, the thermostatic charge is also 35 degrees. Looking at the tables, we can see that a saturation temperature of 35 degrees corresponds to a refrigerant pressure of 61.5 psi gauge. This bulb pressure is exerted on the diaphragm back at the thermostatic expansion valve. If the evaporator's discharge temperature warms to 45 degrees, the bulb temperature also increases. When the bulb temperature increases, some of the liquid evaporates and becomes a vapor. The additional vapor increases the pressure of the liquid-vapor mixture. The new pressure exerted on the diaphragm is 76.1 psi gauge. If you are like me, it will probably take you at least 3 times before you feel comfortable with how this control works. But let's see if we can walk through a few examples to clarify the dense material we just presented.